Okay, the next topic is with developing rating curves. So, developing a rating curve is also one most important parameter in water resources that we can easily do in Excel. Okay, so these are the given data, observed data, H, and the respective discharge at that particular point. So we have two different methods to develop rating curves. One is a trial and error approach, which is a least square approach, and the other is a graphical approach. And anyways, the general equation is given as C H plus A raised to N, where C, A, and N are variables, are constants that are that we can randomly assume and iterate them and find the optimal ones. So these are C, A, and N, so you randomly assume them with certain values. Okay. And then depending on these randomly assumed values, we will calculate discharge, which is Q estimated, and in a meter cube per second. So from this, we use this equation itself, like this discharge is equal to C times H plus A and raised to 2, raised to N. And our C, A, N values are a constant throughout the data. So if you want to keep a value constant, you have to do something in the Excel. So for example, if you want to keep a column fixed to D, then you have to put a dollar sign in front of the D, because columns are represented with alphabets and rows are represented with numbers. So if you put an alpha, the dollar sign before your alphabets, it means that the data should be fixed to this column. And if you put the dollar sign in front of a number, which means the data should be fixed to this row. But if you do the same at the same time, if you put dollar sign in front of your column and in front of your row, which means you are talking about specific cell. So it is D1. Okay, so this one for C is a constant value or constant cell. To manipulate or to calculate all the data up to the observation point. And the same is true for these ones. Okay, if you say F4, you can simply fix them and say is equal to, and if you double click here, you have the calculated value. Now we have to find the difference between the estimated and the observed one. Okay, the Q error, this is an error, okay, which is equal to Q actual minus the Q estimated, because the Q actual is actually measured discharge and the difference should be the error. So this is equal to the actual one minus the observed one. Then you calculate that for the whole observation points. And then some errors are positive, some are negative usually, and so we have to take the square of error. Okay, square of error, which means it is equal to this one square or raised to 2. So this is your error, and then you have to take the sum of square of errors, and you go this, and by selecting the row, the column as a whole, and then you say sum. Then this is square of errors. This is sum. This is sum of error square. This is sum of error square, and what we are going to do is we have to use some function, the optimization function, that can minimize the error and then give us the value that minimizes the error. And we use to find that function the solver, and you can go to data, and here is my solver. If you don't find your solver here, you have to go to file and options, and then look into add-ins, and then you have to get if it is added. If you didn't add it yet, you have to get the solver IDs in the inactive IDs list, in this one. So once you find them, you have to select that and say go, and it will install it in time. For example, mine is active, so it's already working, so it is in active application. Okay, so once you find that, and go to solver, okay, and set your objective. So our objective is to minimize the total error. Okay, so this is the square of errors, and our objective is to minimize that square of error. So I select this cell as my target cell, and the objective is to minimize this value, and the parameters to be manipulated are C, A, and N, because we assume this randomly. So by manipulating this one at the point where we obtain the square of error very minimum, so that is our C and A and value will be estimated that way. So you say okay, let's solve it. And this is the first iteration. So with the first iteration, this is 300, this is 302, this close, and this is also good, and this is also good. So we can try another step. So for that, you use the same data, go to solver. So you'll use the same input data and then say solve, and you can check your values. And the others are getting closer and the others are getting farther. Try that up until you see no value being changed. Okay, for example, this is 303, this is 275 to 32. Let's see if they can change with this iteration. So now look at them. Okay, they are not changing, which means this is the optimal values of C, A, and N. And if you want to check how good the estimation are, or how good the estimated graph is, you can just go to insert and plot a curve, and say add your data. Okay, this is observer 1, and the x value is the observation number. And you have the y. The first time your y is actual 1. Okay, and second part is you have to add the second data. Okay. Say add, and the x value is still the observation number. Okay, and sorry, this is estimated one, and the x value is still the observation number. Okay. And the y value will be estimated discharge, and then you can see how close these two graphs are. Okay, if you see this, it is nearly a perfect fit. So these values are good enough to represent our watershed. So we have to write our discharge equation as this equal to C, which is 12.54 or 55, into H plus A is 1.608 raised to 2.77. So this is our rating curve equations, which means after all, if you have an observed head data at your watershed, and you only need to come up with H, and you can substitute H, and you can estimate your discharge. And this is how we develop rating curves, by using least square approach or trial and error approach.